Hello, in this lecture I'm going to talk about a class of reactions that is very common to carboxylic acids and especially carboxylic acid derivatives, and that is nucleophilic acyl substitution. Okay, and the acyl part is really important because that helps differentiate this from the nucleophilic substitution we learned about in first semester of organic chemistry. In that case, we were learning about SN1 and SN2, so unimolecular and bimolecular nucleophilic substitution. And those occurred on alkyl halides. In this case, these types of reactions are occurring on acyl halides. So imagine a carbonyl separating the halide from the R group. And now you've got an acyl compound. All right. So I want to first make a comparison. So with ketones and aldehydes, they tend to undergo a class of reactions known as nucleophilic addition. Okay, and in nucleophilic addition, what we had something like this, where Y equals R or H, and maybe I'll say R prime. Y equals R, we have a ketone. If Y equals H, we have an aldehyde. Okay, and that would react with a nucleophile, and we'd have some number of steps. And what would happen is the nucleophile would add to that carbonyl carbon. At some point, we would probably have a proton transfer, but the Y group would stay there. Okay, and that's because H or C here, they're going to be a poor leaving group. All right, H minus or C minus, those things are very basic, which makes them poor leaving groups. Okay, now let's imagine a different situation here. All right, now we're going to change Y, and Y is going to equal a good leaving group. Oops. Okay. Or good enough. Whether or not it's good depends on what type of reaction. Okay, the reason I say that is OH minus is a good leaving group for nucleophilic acyl substitution, but not for SN2. Okay. All right. And so if Y equals a good leaving group, okay, now we're dealing with carboxylic acids and their derivatives. Acids / derivatives of carboxylic acids. Derivatives. Okay. And in this case, now we're going to have nucleophilic acyl substitution. Okay, something's getting substituted. All right. And what's happening in nucleophilic acyl substitution is our good leaving group, our good enough leaving group Y, is going to get substituted now with the nucleophile over several steps. Plus Y minus. Okay. So, yeah. So you can see something different is happening based on how good of a leaving group we have here at this acyl position. All right, and let me give you an example of this, of a nucleophilic acyl substitution. And that's going to be base hydrolysis of an ester. Okay. Now, nucleophilic acyl substitution, just like nucleophilic addition reactions that we saw in chapter 18, can occur under basic or acidic conditions. And it's really important to be able to recognize, are we dealing with basic conditions or acidic conditions, because it changes the mechanism and when a nucleophilic addition happens versus a proton transfer, and whether or not we've got a negative charge in there or positive charge. So really want to be careful about that. Okay, so in this example, and I'll try to keep this a simple ester. Okay, ethyl acetate, ester. And basic conditions, NaOH. So remember, this is the spectator, the sodium, OH minus. It's going to be as a base, okay? And then we usually use this with water. And what this will give us is a carboxylate, okay, sodium carboxylate plus OET plus ethanol. Okay, and I'm going to explain why that is in a second. Sodium acetate, there we go. Struggling with the name there. Sodium acetate plus ethanol. Okay. This is a three-step mechanism, so let's talk about what happens. All right, and there's 3 steps in this mechanism, and you know all of them. You've seen all of these elementary mechanistic steps before, believe it or not. Okay, so let's start here. So I want you to pause the video at this point and see if you can figure out what the first step is, because I bet you can. All right, so I'm going to show you what this next step is, or this first step. We've got a lone pair nucleophile. We've got an electrophilic atom here on this carbonyl. So we're going to have an attack on that. That's going to be a nucleophilic addition step. Nucleophilic addition. All right. All right, and that gets us to this intermediate. Please show all your lone pairs on your intermediates and the correct formal charges. All right, we call this a tetrahedral intermediate because we go from having a carbon that is trigonal planar, sp2 hybridized, to being tetrahedral, sp3 hybridized. Okay? We have a good enough leaving group here. So our second step is that it's going to leave. All right? And that is called a nucleophile elimination. All right, and that gets us to, at this point, we have a carboxylic acid plus OET. All right, and don't forget there's a sodium that's acting as a spectator to all this, a sodium cation. Now, this is a good point for us to apply some of our knowledge of acid-base chemistry. So you might recall from our previous couple videos that acetic acid has a pKa of about 4.7, 4.76, depending on who you talk to. And ethanol, the conjugate acid of ethoxide, has a pKa of around 15 or 16. All right. What that means is that we're going to have this is going to pluck off a hydrogen. Okay, and that pair of electrons goes on to the oxygen here. Okay, and the equilibrium is going to favor this direction. Right, and we get this acetate ion plus ethanol. Okay, and just as a review of why that happens, this is a proton transfer. This has a pKa about equal to 15. This has a pKa about equal to 5. This equilibrium favors the weaker acid. Okay? So in summary, for this particular nucleophilic acyl substitution, we have a nucleophilic addition followed by a nucleophile elimination followed by a proton transfer. I think it's safe to say that all, or most, maybe I'll hedge my bets a little bit here, nucleophilic acyl substitution reactions have a nucleophilic addition, they have a nucleophile elimination, and they may or may not have a proton transfer. Okay, and the order of these steps will often depend as to whether we're under acidic or basic conditions. All right, that concludes our introduction to nucleophilic acyl substitution reactions. I believe in our next video we will look at a nucleophilic acyl substitution under acidic conditions, which is the acid catalyzed Fischer esterification. All right, thanks for watching.